Morning, everyone. It's a great pleasure to be at this double 60th birthday of Eric and Mike. I've known both of them for, I think, well over 30 years. I know Mike better. This means that I have lots more embarrassing stories to to tell about Mike. I'm not going to do many. I just we really have known each other for so long, and actually, my wife Edna, first of all, she introduced Mike and me. She said, "You're going to be great friends," and she was right. And then we introduced Heather to Mike, his wife, to him in Eugene, Oregon, a few years later, and yeah, the families are really closely connected. One story I wanted to tell, because the good advice for a graduate student, is a story of how Mike decided to do combinatorics. Now, of course, he will tell you that's not the real story, but today there are alternative facts, and this is I think it's for the graduate students here. Mike was a graduate student at MIT. He didn't know what area to do his PhD in. He was talented in all, as you know, and he was just listening around to the conversations of different groups of people in the corridors, and in order to see what fits him best. And when he was near the algebraists, the typical conversation in his condensed version was, one would say to the other, "You remember this really extremely general result I proved last year? Well, guess what? I now generalized it even more, and I can prove an even more general one." And okay, that was their spirit. And then he hung around with the combinatorics a little bit, and the type of conversation he would hear is, "You remember this trivial problem I told you about last year that I couldn't solve? Well, I found a special case that I can still not solve." So he decided that's for me. For those of you who worked with Mike, actually know that he still has some affinity to the algebraic side, in that I mean, yeah, there are some people who worked a lot with Mike, and he has this tendency, whenever he's facing a problem, the first thing to do is to just generalize it as far as possible, just below, just to where it becomes false, and then scale it a bit. It's been great working with Mike. We have many papers together, and actually the story I'm going to tell you today is, you will not see the connection at all. This is a problem that Eric cares about, Mike cares about, and lots of people care about. This is a PIT problem, or polynomial identity testing problem. This is a thing that started me on this journey that is leading to the work I'll talk about here. I just want to mention, so this problem is the problem of testing algebraic identities. What I'll talk about today is testing inequalities. I just want to mention that Mike and I spent something like 5 years of work on this, meeting every week in a cafe for the day. We had lots of great ideas that ended up with nothing. I think that's a story of lots of other people who've been working on this problem. So I'm not going to talk about this. I'm going to talk about the Braskamp-Leib inequalities. And this joint work with Ankit, more visible, yeah. Let's see, you'll tell me when it becomes best. Is this? Ankit Garg, Leonid Gurvitz, and Rafael Oliveira. And this work that we've been doing for the past 2 or Rafael 3 even years, the buzzword, the main buzzword that I'll actually not mention, that Michal mentioned, is operator scaling. That's behind the scene here. And we have a couple of papers on this, and there's more coming. And what I'm going to tell you today is about these inequalities. It's an interesting field that connects, as we will see, algebra, analysis, optimization, and what we will not see is complexity theory and other areas of math. But we will just quantum information theory. But we will just see this algebra analysis and optimization. So let me start by just, before stating what these are in general, just telling you about some inequalities that you have seen. Actually, even before that, let me just say, this is a family of inequalities. This family of inequalities generalize lots of inequalities that are used in analysis and are used in mathematics all over the place, and some of you have used. Maybe I'll write a few. Cauchy-Schwarz, Hölder inequality. We'll see some of them. The hypercontractive, the Nelson hypercontractive inequality. Loomis-Whitney. Very important inequalities. The Brun-Minkowskis. I could go on and on. I mean, there are lots and lots of inequalities proved in very sometimes different areas of mathematics that all fall into this heading. And we are just trying to understand them better. They were, understood. I'll tell you some of what was understood about them. And but before we get there, I want to, in order to introduce them and the important parameters that they have, I want to give a few examples. So let me start. Questions, please feel free to ask. It doesn't seem like a computer science talk. There is a main computer science component. The main message of the talk is a new polynomial time algorithm for problems that arise there, and also connections to optimization that I believe, will be useful to our field. So, so just some examples. Probably I'll spend 10 or 15 minutes on examples. So what is Cauchy-Schwarz inequality? Let me write it down. So Cauchy-Schwarz inequality. The integral, so we have, let's say, two functions, f1, f2, from R to, let me say, R plus, and integrable. All the function I'll talk about will be integrable. So the integral over x, f of x, f1 of x, f2 of x, is at most f1. Okay? Everybody is happy with that. I don't write the x's, excuse me. The thing I want to point to in this are these numbers. So these are the norms, right? The two norms. So when I write f alpha, I'll just, this is just the integral f of x to the alpha. Right, the usual definition. And the question we will ask ourselves is what kind of norms you can put in these inequalities. The left-hand side will always be like an integral of a product. And we will ask ourselves what kind of norms we can put there. And you all know that actually another really weird thing about this field, even though it's analytic field that deals with inequalities and norms and everything, they somehow call, so you should read this half as 1 over 1/2. For them, LP is L1 over P. It's just a matter of notation, but it's sometimes confusing. Anyway, the question is what other numbers we can put here. And there is a Hölder inequality. I'm just trying to give some intuition that says the same thing under the same f1 of x, f2 of x. f1, 1 over p1 times f2, 1 over p2, for every p1, p2, such that p1 plus p2 equal 1. Right? That's the Hölder inequality. In fact, you can generalize. You can write the integral of the product of fi. If you have more functions, it's OK. You can write that this is at most the product of these norms, fi 1 over pi, as long as the sum of these pi's is 1. OK, everybody's familiar with this. Let's go up some dimension. Again, any questions? These are special cases of what we will see.
Is that the exactly one, or is it bounded by 1 in one direction?
What?
Is that the exactly one?
Yes, exactly one.
So it can't be lower?
No, and that's, yeah, and I'm asking you to pay attention to these numbers, to these pi's. They'll be all over. So let's go up one dimension. Here is an inequality, an easy inequality that you know. Suppose I take here some region, A, and I project it to the x1 coordinate and to the x2 coordinate. Right? So it's obvious that the area of A is at most the product of the projection on x1 of A. And, just the length. And I claim it's an inequality of the same form where the fi's, like f1, is simply the projection, just a projection onto x1 of the characteristic function of this A. And if you write it like this, what you see, I'm not going to be formal about it, but you see that here you can take only the one norm. So really P1, I'm not writing in this form, but R1. OK, if we go up one dimension, there is a more interesting inequality.
No, wait, Avi, then this doesn't fit your standard.
Yeah.
It actually does.
How? You want P1 plus P2?
What do you mean? That's a different, it's not Hölder inequality, that's a different inequality. It's a different inequality. I moved up, forget. I'm giving you lots and lots of inequalities. And here's the more interesting one here is when we go up one dimension and we take 3. So here we already generalized something. Here we had functions, fi are functions from R2 to R plus. These projections, right? Let's take now functions fi from R3.
Avi, I'm sorry to bother you again, but no, in your definition, fi's are functions from R to R plus.
This function is on the characteristic function of the set A is 2-dimensional. This is the function, yeah?
No, where is f1 defined and what values does it take? I see it as a function of the 1-dimensional, but how do you want to do it in 2 dimensions?
It takes the input to the function is a point. I project it to the, I project the characteristic function. Yeah. And now I'm going to do the same. Suppose I have here, maybe I'm not sure how this will end, but I'll try to draw something. I'm trying to draw a body in three space, and now let me project it in these three directions. I project it, in this direction, in this direction, and in this direction. And I'm getting some, can you see this? I mean, does it make sense? Yeah. And, okay. And there is if this is some, body S, the inequality that goes in here is the volume of S is at most the projection x1, x2 of S. So the products of these, these are the products of these areas, so I guess area of the projection of S to x1, x2 times the area of projection x2, x3 and the projection of the area. Similarly, but you have to put it here some exponents, 1/2, 1/2, 1/2. So in this example, P1 is P2, is P3, is 1/2. And again, it's tight. I didn't say all these inequalities are tight, so there are constants here. Maybe this is constant 1, this is constant 1, this constant is 1, this constant is 1. This, you cannot put a better constant, and you cannot put other exponents, other norms than what I have said. So here you are very rigid. Somehow you can only have a particular set of norms, whereas here, you have lots of choices. Also here with PI. Okay, let me just give maybe a couple more examples. By the way, these are, some of you know them as entropy inequalities. This inequality, so this is Loomis-Whitney. It's a special case of Loomis-Whitney. And some of you may know this inequality in entropy form as follows. Maybe I'll write with a better pen. Right? This is the same inequality, really. And there are generalizations to this, which I probably will not write down. Some of you know it, and some of you don't. Inequalities of entropy that are much more general. Shearer's inequality is also a special case. Okay, maybe I'll do just one more so you see how interesting it can get. I went up dimension, but we can stay even in 2 dimensions, but just project on more directions than 2, not just the orthogonal projections. And there is something called the Sharp-Young's inequality, in which you do the same pictures as there. So you have some region in the space, some area A, and you project it here. You project it here. And you also project it along this line, which is, so this is x1, this is x2, and this is x1 minus x2. So you also project it here. You can do it formally, right? You can look at the length. And what's the relationship between the area of the 3? Well, it turns out that the area of A is at most square root 3 over 2 times these, the norms of these three functions. Maybe I'll just, the projections. So Fi is a projection on the appropriate direction of 1a. So times the 3 times the product, 3 of these norms, fi, when you take it here, I guess I called it 3/2. So here there are numbers, so you can take pi to be p1, p2, p3 equals 2/3, and then you get this constant. And the question is whether this is all you can do. We saw there it was very rigid, here it was more flexible. What happens here? Well, here you can take other things. Turns out that if you can take any, as long as p1 plus p2 plus p3 is 2, and the pi's are at most 1 and at least 0, it works. But with some other constant, with this constant here is going to be something like, not something like, I think exactly, the product 1 minus pi, 1 minus pi, over the product pi, pi. Mysterious. That's the Sharp-Young inequality. And these are, all these constants are tight, and that's all the, if you try any other pi's, there is no inequality. And in all of these cases also. So what's going on? So far, so good? Just
So Avi, here the extreme examples are boxes. That show. What's the extreme example here? You don't know?
No.
And no one knows?
I don't know if no one knows. Maybe Young knows. No, I didn't look into it. I didn't look into it. Let's talk about, you'll I'll give you a more general answer that will include this. Yeah, I will give you, wait a minute, wait 5 minutes, I'll tell you. For this particular one, I don't know, but in general, I know. In fact, Lieb knows. So, okay. So now what's going on? Is this visible? Oh, no. So I'll go back to purple, even though it's sort of monotone. Okay, so what's the general form, first of all? I want to write the general form. These are the Braskamp-Lieb inequalities. From, I think, 78, and the important paper really is Lieb 90, in which it appears in the generality I will write, and also understood much better, is the following. You have, so you want to understand all these, we projected in all sorts of directions. Let's just give it names. So the data for Braskamp-Lieb inequality is a bunch of projectors or linear transformations. You have Bj, so we'll have m of them, maps from some whole space, Rn, into some lower dimensional space, n sub j. They don't have to be the same. You can project here in 2 dimensions, here in 3 dimensions. So a bunch of this and a bunch of numbers, as we saw before, Pj's. And the inequality, true or not, what you would like to prove is that the integral of the product of the fi's, x in Rn, is at most some constant, that you want the best constant that you can, maybe there is none and it's infinity, times the product of these norms. Okay, that's the Braskamp-Lieb inequality. And the question is whether it holds. So what are the big questions here? The big questions.
No. What's the connection?
B or B?
What are these betas or b's doing here?
Yeah, they are. Oh, wait. Very good. I didn't. You cannot apply fi. I'm sorry, man. Very good. You cannot apply fi on x. You apply it on. Thank you. Fj. Bjx. So you project x down, and then you can apply f to it and integrate. Yeah, so, okay. And what do I want? What do I mean when I want it to hold? What are the f's that it should apply to? Like in all the other cases, it should apply to all f's. So this should hold. You want this to hold. This should be true for all functions fj from R and J to R plus, integrable. I give you, so the data here is B1 through Bm and P1 through Pm. And the question is, given this data, in all these cases, I gave you specific Bs and specific, right? These were project, yeah. So the question is, when is it true? All of these are special cases of this. Okay, and the question, when do you get an inequality? So the basic questions are, when is C finite? What is the best? In this case, what is the smallest? And in all these cases, I told you the answers to those questions. Okay.
So are we restricting the B's, the Bj's in any way?
No.
No.
For any set of linear transformations, you can ask this question. Yeah, there are linear transformations. Sorry. No, of course not. There are many I will not explain, and some are more complicated than others.
So phi, and that it's linear, it means that, for instance, this on the left side, so it's true for the 60 degrees triangle.
You can draw lots of lines in all sorts of directions and projects, and something is true. Something is true. Yeah. But there are cases where this is infinite. There is no bound, right? If you change in here, in the first trivial example, you change the PIs, it doesn't hold. So it depends on the linear transformations and on the.
That's the business of the rigidity that you mentioned. Sometimes it works only for some parameters, it simply doesn't work for others.
Yeah. Yeah, and you will see exactly when it will. You like it or not. You're just. Yeah. So these are the main questions, and they have answers, beautiful answers. Structural, so not computational, but structural. And let me first give you Lieb's answer. He characterizes this by a program, unfortunately a non-convex program. Okay? So he says, so the minimum, so let's call this, the smallest c is called the Braskamp-Lieb constant of B and P, of this data, right? The B's and the P's. The smallest constant you can have. And he says that if it's finite, well, anyway, you just have to do the following. Let me write square so I don't have to write square roots. It's a supremum over all positive definite matrices Aj, which are of dimension n sub j, of the following ratio. Here you have the product of determinants of Aj to the Pj. And in the bottom, you have the determinant of the sum. You have to, excuse me, there is a formula here. Bj transpose or dagger Aj Pj. You don't have to remember it. It's not going to be in a quiz. It's just an optimization problem in which the variables are some positive definite matrices. If you optimize this, if the optimum is infinity, then there is no inequality. If the optimum is something, that's the optimal constant. I'm not going to explain this, but I'll just say one word about the consequence, or about the proof, is that this formula comes from a very simple origin. What Lieb actually proves is that the optimizers, the worst possible functions here, are Gaussians. Are Gaussians with covariance matrices A sub j. And the question is, which Gaussian distributions are the worst? You optimize overall. That's the A's. The A's define the Gaussians. So that's where it comes from. And so I want to point out that A, it's an amazing result. You understand it completely, in a sense. And the only unfortunate thing is that this is a non-convex optimization problem. And our main result is that this problem is in P. So that's the main theorem.
It's non-convex only in terms of the objective function. The A is the cone of semi-definite program.
Solving this problem is a non-convex. It's non-convex in the variables. It's not a convex. It's a ratio of.
Yeah, just the objective function, but the domain on which it's is convex.
The cone of positive. Yeah. Sorry, I didn't understand. Yeah, the domain is convex. Yeah, the objective function is not. And despite that, we solve it in polynomial time. So we can, for any, you give us the data, we can tell you if there is an inequality and what's the best constant. That's one characterization. And that's one, because there is a solution here to a non-convex optimization problem, we think a polynomial time algorithm for non-convex, we believe that this should be powerful in optimization. We are exploring this and, anyway, that's one way in which to sell this algorithm. It solves some seemingly complex family of non-convex optimization.
So it's non-convex, but does it have local minima that are, does it have any non-trivial local minima?
So super
It's,
maximum.
I mean, maxima?
I don't know. Let me,
Okay,
Yeah.
just
yeah, it's a good question. Let me now tell you another characterization of the when is an inequality possible, and this is due to Bennett, Carberry, Christ, and Tao. And it's the following. It's a linear programming characterization. So what's a linear program? I have to give you a linear program that from this I have to generate from this a linear program, and its feasibility should tell you whether there is an inequality. It doesn't tell you what the constant is, but it still tells you at least answers the first question. And this is the following. The variables of the linear program will be the p's. When it's satisfied, these p's have an inequality, otherwise they don't. So you want two conditions. The sum of pj n sub j is n. This is a scaling. You just want this inequality to scale if you multiply things by constant. So that's easy and forced on you. And the other, which is clearly a necessary condition, again from scaling, but it's not clear at all that it's sufficient, is that when you do the same for, so it's a generalization of this one, dimension of b sub j v, I'll write it and explain, that's at least a dimension of v. And this should hold for every subspace V of Rn. Okay, so again, you take an arbitrary subspace of Rn. On the right-hand side, you have its dimension. On the left-hand side, you have a weighted sum of the dimensions of what happens to the subspace after you apply the linear transformation to it. Okay, so you get other subspaces, and you count their dimension. This has to happen. If you see it for the first time, it may look weird. I want to point out two things. Even though there's potentially infinite or uncountable number of subspaces, because the numbers that appear here are just integers between 1 and n, there are at most exponentially many constraints in this linear program. It's most exponentially many facets. So it's a linear program. It's exponentially big, and its feasibility determines whether there is an inequality or not. So this result tells you that we can solve this linear, we can have a membership oracle for this linear program, despite the fact that they are.
C doesn't come out, the constant doesn't come out.
No, the constant does not come out of this, So we can do it too, but it comes out of this. So there is a family of exponential size linear programs that we can solve in polynomial time. And the question is, what are they? Or can you embed nice combinatorial problems in there? And I'll give you a couple of examples of this. So again, so the main message I just want, because it's not clear when I'll have to stop, there is a polynomial time algorithm that solves non-convex programs of this sort, solves exponential size linear programs like this. I should add that we also know how to give also separation oracle here, and in fact can even do optimization. But I will not get to this.
So these are not obvious. You have to come up with hard subspaces and so on.
No. So I want to say something about the algorithm.
So is any of the two, membership and separation, is any of the two easy or both you have to work? For the linear program.
One direction is easy, to show that,
That these are necessary, right?
yeah, necessary and sufficient. If you have a subspace
Necessary.
in which it is bigger, then you can see that you can easily violate this. So that's one
No,
direction.
I'm talking when you try to solve this exponentially large.
It's not even clear what the linear program is, the way it's given. It's not even clear which inequalities participate there.
But
Because
probably,
there are continuously many
No, but,
subspaces.
so just when you say this is a feasibility problem,
That's a feasibility.
and I think what you're, even given a potential, a point, knowing whether it's feasible, just testing.
Yeah,
That's the hard problem.
That's a hard problem.
Yeah.
Solving just feasibility for this is the determination of whether an inequality works at all with some finite points.
No, I give you P's. So condition
You
one
give
is
me
very
P, yeah.
condition one is very easy to check.
Membership is yes. Sorry, I didn't answer you right. Sorry. Membership is non-trivial.
Okay.
Because what do? I mean, there are exponentially many inequalities.
so probably what happens is that, so the first one is kind of necessary, and then the second, if the beta j's are random, then probably the first one is already enough.
No. That's very naive. That's not true. That's not true. I mean, just consider the examples I gave. Right? I mean, which P's are feasible? You saw that it's, and they are just, they were for very simple B's. I want to tell you in the last 10 minutes maybe a hint about the algorithm, where it's coming from, what's its nature. Okay? More questions? So it turns out that there is a very important family of Braskamp-Lieb inequalities called geometric Braskamp-Lieb inequalities. That was introduced by Boll and by Barth. And there the B's have some special properties. One is that the B's are, you can say, are projectors, by which I mean simply that BJ transpose, it can be over the complex, it can be transpose conjugate, are the identity. So all of them, this for all J. Okay, it can happen. In fact, many of the examples we saw, it does happen. And the second is that they are in general position. They are isotropic. And by this I mean that when you sum up Pj, and now you want to make them all of size n, remember you think of them like this, Bj is nj by n. And now when you do Bj transpose Bj, so this is identity on nj, and this is identity on n. It's a general position. I can mention that in the case that all nj's are 1, this is called the rank 1 case. All these are vectors, right? Then Bj's are really Vj's. And this should remind you some of
Sorry, Avi, is there any connection between these P's and those P's?
These are the same p's. These are geometric. So you are given b's and p's. And I call them geometric if those two conditions hold. Okay? It's a sort of nice data. In the case, I just want to give a simple example. In the case that these are vectors, right? All of these are vectors. Then this should remind some of you of the geometric position here. Should remind some of you the sign rank result of Forster, because what this says for vectors is simply that they are unit length, and what this says is that they are isotropic. There, the PJs are 1. So it is related. It generalizes that result in an interesting way, but I'm not going to get there. I mean, it's just natural and nice kind of family of B's and P's. And the important thing, the result of Barth, I guess, is that in this case, in the geometric case, the Braskamp-Leib constant is always 1. So it's always doable, always, there's always an inequality, and in fact, always with constant 1. And that explains many of the examples I've shown. Okay. So the starting point for us, in order to have an algorithm, is to say, well, maybe there is a way to make we start with an arbitrary BL data. We have B and we have P. Right? We are given that. We want to know if it's finite. We want to know the constant. We know that if it were geometric, we would be done. Maybe we can get it to be geometric. Why not go there? So let's do it. Let's make it geometric. The crucial observation is that you can easily enforce property 1 or property 2. How do you enforce it? Well, you want the projectors to have this. If for some reason BJ transpose is something else, let's call it CJ, then you simply move to BJ prime, which is CJ 1/2 BJ. And after that, of course, BJ prime minus 1/2. BJ prime transpose will be the identity, right? So do it. So here's the algorithm. The algorithm is extremely simple. Iterate T times. If it's not invertible, then there is no inequality. Very good, very good. I'm going to tell you. Let's do it here. When you do this, you can easily check that the BL constant of, well, let me do it. Let me do it here. The constant is changing by the determinant of the matrix you multiply, simply. So B prime P is simply the determinant. If you do one step like this, Cj, and now I'm not sure I'm writing it maybe 1 over. It's important, it's just that I'm not sure I want to think about it. So that's a very good question, and I was going to say the important thing about these changes is that you can keep track of how the constant changes by the determinant of the change you are making. And similarly, if this is, that's so you can make the condition for all of these. Sorry, I wrote the algorithm. Let me write the algorithm here. Algorithm, iterate T times, and no, sort of enforce 1. And force 2. So you fix this. This may not hold. Then you want to fix this. You'll see that you just have to multiply all of them. You have to take all the B1 up to Bm and multiply on the right hand by a single matrix C in order to fix this condition. I'm not going to write it down. And then again, the constant changes by a determinant. So
How is this related to matrix scaling?
this is matrix scaling. This is operator scaling. Yes, very good. So I have to finish in, 3 minutes or 4 minutes? What? Yeah. So I'll stop writing and I'll just tell you. This kind of algorithm where you optimize one side, then you optimize another, and it's not clear it's going anywhere. It's called alternate minimization in the general optimization literature. Sometimes it's a good idea, sometimes it's not doing much. In this setting, it turns out, I mean, you have to prove it, and this goes back to work of Sinkhorn on matrix scaling in the 1960s, and in particular for me, work with Nati Lineal and Alex Samorodnitsky on matrix scaling, where a lot of the understanding and our way of analysis that affected the previous paper with my co-authors here on operator scaling and then affected this is the same algorithm. At the end of the day, the analysis rests on two things. One is easy, and that was the same as it was there on the MGM inequality. You squeeze it, it's such a, and Nati knows why it is. I have a warm feeling towards this MGM inequality from my high school days. But the other thing that I have no time to tell you about is, how do you analyze this? There is a 3-step analysis to it. You know that you cannot, it turns out you cannot reduce this Braskamp-Lieb constant below 1. These iterations at every step reduce it a little bit, but non-trivially, every step. That's the AMGM inequality. And the last step in any analysis like this, you just want to say that you don't start too high. So you need an a priori upper bound on this number. So you want from just the given data, B and P, to have some upper bound here. And the main part of the theorem is proving an exponential, is to prove this theorem. And just the last word is about the source of this theorem. It's not clear. I mean, these analysts, of course, were interested to get a priori, to get just bounds on the constant if it's finite, and there were no arguments. They were using just compactness arguments, basically no effective bounds. The reason we can do it is because there's an algebraic structure here. There's a group action here. You can use tools of invariant theory, some of them very deep, in order to get this. And I don't have time to explain to you this part, so I'll stop here.
You mentioned about applications where you can embed some of the combinatorial product in this exponentially long list.
Yeah, so one really simple one is matroid intersection. It turns out that the, maybe I shouldn't, what?
Go ahead.
Yeah. Okay, so.
You should mention that there will be a seminar on this on Monday here in the discrete math seminar.
On Monday here. Okay, so I don't know. I'll be in Berkeley.
Either Monday or Wednesday.
I'll be in Berkeley. So let me tell you, let me just write down the polytope for matroid intersection, and I'll just claim that it's a Braskamp-Lieb polytope. Okay? So that's the most complex we know, and that's a solved problem. We are looking for applications where it's not. But you are given two matroids. What are two matroids? Two sets of vectors. So maybe V represent, yeah, these are linear representable matrices, Vj and Uj. And you want what you're looking for is an independent set, so a set I here, such that the U's and the V's in this subset are both linearly independent and are of the maximal size. Let's say this is n by m. Then you are looking for a set that's independent of both. That's a linear, the matroid intersection problem. And it turns out that the polytope, the convex hull of all these solutions, of all these i's, the solutions are simply, so we are living in m dimensions. We have P1 up to Pm greater or equal to 0. And it turns out that what characterizes this is that for every j, well, let me not write. I mean, you just have, it's subspace conditions. It's subspace conditions. They just say that for every set, for every subset here, j, what you want is that its dimension will be at most. So basically that they will be independent. You just write that the dimension that's spanned by a set of vectors is the size of the set. So you can stare at it, and then you see immediately that it's a special case of a BL polytope. So you get some of the inequalities. What you have to prove is that the others don't matter, don't change the body.
What do you mean BL polytope? BL polytope is something like this. N at a time.
Yeah. So what you get is equations like this for some v's. And you have to show that they are all that you have there. So let me not write it. But anyway, that's the most complicated. We know a really great challenge that we are thinking about is maybe, so bipartite matching, of course, a special case, maybe general matching.
Can you get every, say, linear relationship among entropy from this?
No. There are even simple ones that you cannot get, like the submodularity, I don't know, h of x, y, z plus h of x is at most h of x, y plus h of x, z. The left-hand side is not of the right form. Right? We can only, so all the entropy inequalities that Braskamp-Lieb generates, on the left-hand side, you always have h of everything. Okay? So you cannot get, that's a very interesting, I'm not, it's possible that these tools can help, blah, 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 but yeah, it's a very good connection. There, the non-Shannon inequalities, there's a long story to tell there, but yeah.
So what do you mean embed one combinatorial code? What do you mean by embed?
So what I mean by embed is the following. You want to optimize over this. You want to find the largest. More generally, so you have a optimization problem. Let's say it's it's some polytope in high dimensions, but unfortunately the number of facets, the number of inequalities defining it, like the Held-Karp relaxation, right, for TSP. Okay, it's just an exponential number of inequalities. It turns out that it shouldn't frighten you, should not frighten you, because maybe this exponential number of inequalities fit in a description of some Braskamp-Lieb polytope, in which case you will be able to do membership, separation, and optimization over this body.
So fit, you mean like just some linear? I don't understand which transformations in the so-called embedding. In which sense?
I'm assuming, let's assume that you have just a linear program, that your optimization problem is a linear program. It's just a linear program, like many of the, only that it's a linear program with lots of inequalities. So, right? So embed just provide the B's and the P's that describe it, right? So if it make it so that the inequalities you have will look like that with the B's and the P's. So we know it only for small, simple examples like matroid intersection. Yeah.
Question. So typically minimize px by qx for quasi-convex functions don't really scare us, right? Because you do px minus lambda qx and then do a binary search on lambda. So why should this form scare us? Because the non-convexity is in the objective.
Here?
So essentially I'm asking, is it possible or plausible that the exponential list of inequalities can be somehow reduced into another convex problem.
I think that there are inherently exponential sized bodies, I mean polytopes with exponential many facets that cannot. In fact, we know all these results about how do you call it? Extended formulation, right? Tell you that like for general matching, there is no smaller, you cannot, just cannot do it. But nevertheless, even this shouldn't scare you because maybe you can reduce it to Braskamp-Lieb polytopes.
Just to make sure I understood the algorithm. So what you're finally stating is the Braskamp-Lieb constant itself is sort of, you're going to use it as a potential function.
Yes.
And state that reduces by a multiplicative factor each time.
Yeah.
And the theorem states that if it's finite, then it is at most as well.
That's right. And otherwise you will run it for the appropriate polynomial number of times and you'll see that you are not close to 1 and you'll know that there is no inequality. Exactly.